Good day everyone, my name is Mohammed Achehboune. I am from University of Sidi Mohammed bin Abdullah, Faculty of Science. Today I am presenting my work entitled Synthesis and Characterization of Rare Earths Doped Zinc Oxide Nanostructures in the first international online conference on nanoscience and nanotechnology. My presentation is divided into 4 parts. I am going to begin by a short introduction. Then we talk about the experimental details. After that, we move on the results. We discuss the results obtained by scanning electron microscopy and X-ray diffraction and photoluminescence spectroscopy. And then we finish the presentation by a short conclusion. So, as you know, zinc oxide is an attractive material of 2,6 group with a wide band gap and large exciton binding. Also, zinc oxide is easily synthesized under several morphologies such as nanorods, nanowires, nanobelts, and nanotube, etc., using different methods and techniques. For example, hydrothermal method, chemical vapor deposition, electrochemical method. However, hydrothermal method is a very simple and easy method used for obtaining nanostructures in a specific shape and size. That's why zinc oxide is considered as an attractive material for optoelectronic devices. Optoelectronic properties of a semiconducting material can be modified and improved by doping process. As you know, zinc oxide has been heavily doped and co-doped by metals such as aluminum, iron, and gallium. But recently, rare earth doped zinc oxide have attracted the attention of scientists research because rare earths exhibit very good luminescent properties owing to their 4F intrashell transition. So, the fundamental aim of this current work is to investigate the effect of ytterbium on the structural and optical properties of zinc oxide nanostructures. For the preparation of our samples, zinc nitrate used as precursor. So 0.1 mole of zinc nitrate was prepared using deionized water. This mixture was heated at 19 degrees Celsius in an oven for 24 hours, and then the precipitate was formed, and after that the obtained material were deposited on silicon substrate and washed 5 times by ethanol and then dried. The doped process followed same steps with the addition of 10% of ytterbium chloride. For the results obtained for our samples, this figure shows the same images of zinc oxide nanorods, as clearly shown in the figure A. The ZNO nanorods having hexagonal shape and the average diameter and length are respectively about 500 nanometers and several micrometers, and with a high density. For the doped material, represented in the figure B, indicates the formation of nanorods in the edges with different size, which means that doping has an influence on the surface of the nanorods. For the results of structural properties of our samples, this figure shows X-ray diffraction pattern of pure and ytterbium doped zinc oxide nanorods. As we can see from the spectra, the presence of hexagonal wall-size structure without any diffraction peaks of ytterbium-related impurities. The results show that the intensity of 002 peak and 100 and now 101 peak decreased with the addition of ytterbium, while the intensity of 100 peak didn't change. So the growth in the directions 002 and 101 is limited after doping, which means that the direction 100 is the preferred orientation for growth in the case of ytterbium doped zinc oxide. In other words, the doping has an effect on crystallinity. To investigate the optical property and effect of ytterbium doping zinc oxide, a room temperature photoluminescence study has been performed. This figure shows the obtained PL spectra of pure and ytterbium doped zinc oxide. It is clearly remarkable that pure zinc oxide peak is more intense than that ytterbium doped zinc oxide. This strong decrease in intensity it may be due to an increase in non-radiative recombination process or to the higher concentration of ytterbium, 10% in our case. To better understand the nature and origin of emissions, this figure illustrated the normalized spectra of photoluminescence. The two samples exhibit two peaks in the visible region. The peak of pure zinc oxide was performed approximately at 560 nanometer, the yellow emission, which usually attributed to the doubly ionized oxygen vacancy. For the PL spectra of ytterbium doped zinc oxide, the peak approximately located at 545 nanometer, the green and yellow emission. This emission comes from the recombination of the holes and the interstitial oxygen ions when electrons occupied the single ionized oxygen vacancy. Also, there is a slight shift to high energies. It can be attributed to the effect of structures which were responsible for the emission in this region. The creation of level by the occupation of the ytterbium atoms, which has limited the emission in this region. In conclusion, pure and ytterbium doped zinc oxide were prepared using hydrothermal method. Structural and morphological properties have been studied using X-ray diffraction and scanning electron microscopy. The results revealed that both pure and ytterbium doped zinc oxide have the hexagonal word size structure with 100 as a preferred orientation for the growth of ytterbium doped zinc oxide. For the optical properties, the PL spectra shows a strong decrease in intensity after doping, with a slight shift to high energies. So this study is focused to reveal information about the optoelectronic properties of ytterbium doped zinc oxide, which may enhance their performance in the photonic and optoelectronic devices. Okay, it's the end of presentation. If there are any questions you'd like to ask, please email me. Thank you.